Last year, global industry emitted a record 37.4 billion tons of carbon dioxide. The traditional method for dealing with this, carbon capture and storage, involves spending a fortune to pump that gas deep underground, generating zero revenue in return. The alternative is carbon capture and utilization, specifically a process called electrochemical CO2 reduction. Instead of burying emissions, this technology treats carbon dioxide as a raw material, converting waste directly into profitable green chemical commodities. This diagram outlines the closed-loop system. We feed renewable energy and raw CO2 emissions into a central electrochemical reduction cell. On the right, these reactions spit out raw products, directly offsetting the need to extract new fossil fuels. In laboratory settings, this creates a profitable green carbon cycle. But if the chemistry is proven and the economics work, there is a reason we aren't deploying these machines globally tomorrow. The technology is currently trapped behind a series of massive engineering bottlenecks. The first bottleneck is physical. Carbon dioxide is thermodynamically stable and highly inert. Breaking the strong bonds between the carbon and oxygen atoms requires an immense input of energy. To force this reaction, chemists use specific electrocatalysts, usually copper, gold, or silver. Their unique surface properties lower the energy barrier required to physically rip the CO2 molecule apart and recombine the atoms. Finding the right metals solves the chemical equation, but building an industrial-scale machine to safely and efficiently house billions of these microscopic reactions per second creates an entirely new hardware problem. The physical engine driving this process is the electrolyzer. To increase efficiency and product yield, researchers have rapidly prototyped and discarded multiple reactor architectures over the last 5 years. This schematic details that rapid hardware evolution. The top row shows the earliest foundational hardware, the 3-electrode cell, the H cell, and the basic flow cell, all of which operate in a liquid phase. The industry had to pivot away from these liquid phase systems because of hard solubility limits. Carbon dioxide simply cannot dissolve into water fast enough to sustain the high electrical current densities required for commercial manufacturing. The breakthrough is shown here in panel F, the membrane electrode assembly. Instead of dissolving the CO2 in liquid, this gas phase setup feeds humidified CO2 directly to the active membrane, eliminating the mass transfer delays and drastically increasing reaction rates. Perfecting this specific gas phase architecture is the critical step required to pull CO2 reduction out of low-yield laboratory beakers and into massive industrial powerhouses. But running the perfect hardware at high electrical currents triggers a war inside the machine. These intense operational speeds cause the catalysts to degrade quickly and promote competing, efficiency-killing side reactions. The highest speed reactions create localized alkaline conditions on the metal. Under these conditions, the CO2 reacts to form solid carbonate salts, physically clogging the diffusion channels and choking out the catalyst. To fight back, engineers apply rapid pulsed voltage drops. These electrical pulses act as a self-cleaning mechanism, blasting away the salt blockages and actively restructuring the geometry of the catalyst surface while the machine is still running. They combine this strategy with extreme pressure. By operating the membrane electrode assembly at 20 bar, they force the salts to precipitate harmlessly away from the active sites. This allows the electrolyzers to run continuously for over 1,500 hours. Stopping the salt buildup, managing high pressure, and stabilizing the metal active sites are the final microengineering victories needed to make these systems commercially viable. The last major hurdle to profitability is the supply chain. Capturing CO2 from a smokestack in one facility and then transporting and converting it in another entirely separate facility requires massive amounts of wasted energy. The solution is integrated capture and conversion. Using amine solutions or molten salts, operators pull dilute carbon directly from flue gas, feeding it straight into the electrolyzer in one continuous process. Once closed, economic outputs scale rapidly. The base tier produces C1 products like carbon monoxide and formic acid. Using copper catalysts, it steps up to C2+ building blocks, ethanol and ethylene for sustainable plastics. At the peak, molten salts form carbon nanotubes, a highly sought-after material. By overcoming these specific, highly complex hardware and chemical bottlenecks, The industrial sector stops treating carbon emissions as an expensive waste management liability. Instead, carbon dioxide becomes a highly profitable, endlessly recyclable commodity. Thank you for watching our video. If you found this breakdown helpful today, please leave a like and subscribe to our channel. This video was brought to you by Synestex Systems LLC and founder Shane Persinger.